Hello, and welcome to part 2 of Multiplying Polynomials, lesson 3-2. We're going to cover examples 4, 5, and 6 now, starting with Pascal's triangle. Pascal's triangle is a famous number pattern named after French mathematician Blaise Pascal. He died in the 1600s. Well, born and died in the 1600s. He didn't even live to be 40. Young fella. So you can use Pascal's triangle to help you expand the power of a binomial in the form a plus bn. That's what part 2 of this lesson is going to be about. So we're going to start by generating Pascal's triangle. You can read. So you can read through that in your leisure. Part A says to complete rows 3 and 4 of Pascal's triangle. In each node, write the number of possible paths from the top down to that node and look for patterns in the tree diagram. So we're going to complete this and we're going to answer these patterns. All right, so when they're talking about paths, they're talking about from here, there's only one way to get to this node. From here, there's only one way to get to this node. From here, there's only one way to get to this node. Or from the beginning, I'm sorry, there's only one way to get to this node. But from the beginning, there's two ways to get to this one. You could go left and right, or you could go right and left. And there's only one way to get to this node. So for this point here, this node here, there is only one way to get there, which would be left, left, left. To get to this node, you could go left, left, right, or you could go left, right, left, or you could go right, left, left. So there's three ways to get to this place. Similarly here, you could go left, right, right, or you could go right, left, right, or you could go right, right, left. Three ways. There's only one way to get here, though. Right, right, right. So completing row 4, same situation. You'll trace over every way you can to get to the different nodes. Or you may already notice a pattern. Hopefully you already notice a pattern. After row 2, starting with row 3, where nodes meet, the sum of those numbers is the number of paths it takes. You're always going to start with 1, and then sum the two numbers above it that make that node. Here, 1 plus 2 is 3, 2 plus 1 was 3, and it ended in 1. So here, 1 plus 3 is 3 plus 3, 3 plus 1, and you're ending with 1. So this says, what is the value in the first and last node of each row? You should see that the first and last value is always going to be 1. And it says for the other nodes, what is the relationship of the value in the node to the two values above it? The value of each node to the two values above it it's the sum of the two values above it. So we should be able to complete rows 5 and 6 pretty easily now. I'm going to start with 1, because there's only one number above it. 1 and 4 together make 4 and 6 together, 6 and 4 together, 4 and 1 together, and there's only one number above that one. Pause and complete row 6. And check it. Hopefully you've also noticed that each of these rows is symmetric. And Pascal's triangle is definitely something that you want to remember how to do, because you can scratch one of these out anytime pretty easily if you know how it works. So please highlight Pascal's triangle, put a big circle around it. That's going to be an important thing for you to make note of. Well, let's use it. And let's see if we can make this video even shorter than the last one. Trust me, everybody wants the same thing here. Okay, for example 5. We're going to use Pascal's triangle and expand a binomial, or look for a pattern anyway. Okay, went ahead and scratched out the reflection problems for 4. This talks about the value in position R of row N in Pascal's triangle is written as a big C, there's a little n before it, and there's an R after it. So in row 0, this first number has zeros on each side of it. In row 1, you have a 1 and a 0, and then a 1 and a 1, and so on and so forth. That's not critically important, I just wanted to point that out. So for example 5 here, we're going to expand the power of a binomial. Anything to the 0 power, hopefully you remember, is 1. Anything to the first power is itself, so these first couple are pretty easy. Now, a plus b quantity squared. You can write out the two binomials, a plus b times a plus b, but hopefully you remember. The first terms, a times a, would be a squared. The outer and inner terms would be a times b and b times a, which will give you 2ab. And the last terms, b times b, will give you b squared. Feel free to go ahead and write out a plus b times a plus b and do the math on that. And it gives you a tip on a plus b cubed to multiply a plus b squared times a plus b. So we can go ahead and do that to the side. A plus b times a squared plus 2ab plus b squared. Also, hope that you can hear me a little bit better this time. I'm trying to talk louder. So I'm going to start by multiplying my a times every piece, a cubed plus 2a squared b plus a b squared. Then I'm going to multiply the b times every term in the polynomial. So I have a squared b, which I'm going to line up. Then I have 2ab squared. And then I have b cubed. So when I combine my like terms, and it was a cubed plus 3a squared b plus 3ab squared plus b cubed. And I'm going to write this over here. Keep everything lined up nice and neat. A cubed plus 3. There's 3 of those. 2a squared b plus a squared b is 3a squared b plus 3ab squared plus b cubed. Okay, so far? Some of you in the back of the class going, no, not okay so far. Okay. All right. To do a plus b to the 4th, and this is the last one of this example that we're going to do, it gives you a tip to multiply a plus b quantity cubed by a plus b. So again, we'll multiply every piece times the a, and then we'll multiply every piece times the b, and we'll combine our like terms. So a times a cubed is a to the 4th. A times 3a squared b is 3a cubed b. A times 3ab squared is 3a squared b squared. And a times b cubed is ab cubed. Let's see that. Okay. Then I'm going to multiply the b times every one of these. B times a cubed is a cubed b, and again, notice I am lining up my like terms. B times 3a squared b is 3a squared b squared. B times 3ab squared is 3ab cubed. And b times b cubed is b to the 4th. Anybody notice a pattern yet? When I'm combining my like terms here, I'll get 4 of these, 6 of these, 4 of these, and just 1 of each of those. Does this look familiar? So I have a to the 4th plus 4 a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Couple of other patterns we want to pull out there. Hopefully you noticed that the coefficients here are Pascal's triangle. You have 1, and you have 1a and 1b, 1a squared, 2ab, 1b squared, 1a cubed, 3 here, 3 and 1, 1, 4, 6, 4, and 1. So hopefully you should be able to notice that if we did a plus b to the 5th, we could predict what the coefficients would be based on Pascal's triangle. Also, the number of terms is one more each time. This is 1 term, 2 terms, 3 terms, 4 terms, 5 terms, and 6 terms. There's always one more term than the exponent. So if we wanted to write this out, we would know that we would have 6 terms. 1, 2, 3, 4, 5, and 6. We could go ahead and put in our coefficients. We know it's going to start with a 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And you just have the 1 there. Also, notice the pattern in the coefficients, or in the exponents. Your exponent is going to start with the exponent that you are working with. So a plus b to the 4th started with a to the 4th. A plus b cubed started with a cubed. So a plus b to the 5th is going to start with a to the 5th. And then notice for every other term, the a exponent goes down and the b exponent goes up. So on a plus b to the 4th, you started with a to the 4th, and then went a cubed, a squared, a, and then there wasn't an a at all. So I'm going from a to the 5th to a to the 4th, a cubed, a squared, a, and then there won't be an a at all there. And notice that after the first term, you start building up with the b's. So there won't be a b in this first term, then you'll have b, b squared, b cubed, b to the 4th, and b to the 5th. Also, notice that the exponents in every term sum to 5. So if we took off these 1s, because you don't really need them, you would have a plus b to the 5th power. To the 5th plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus b to the 5th. So if you know this pattern and you understand Pascal's triangle, then you can find the power binomial pretty easily. So answering the questions here, what do you notice about the exponents of a? And you should notice that they go up or they increase every time. I'm sorry, that's backwards. Those go down. The exponents of a are decreasing. The exponents of b are increasing. Okay, so the exponents of b go up or they increase. Exponents of b go up. And it says, what is the sum of the exponents in each term? Well, if you're talking about a plus b to the n, then the sum would be n. Because when you're talking about a plus b to the 5th, the sum is always 5. A plus b to the 3rd, the sum is always 3, and so on and so forth. And it asked, what is the pattern of the coefficients in each term? And we noticed that they followed Pascal's triangle. They follow Pascal's triangle. Feel free to pause it if you need to get this on your paper or soak it in. You can rewind it, watch it again. It's a very cool, interesting, and neat pattern for those of us that enjoy puzzles, enjoy patterns, which is all that math is. If you can learn to love puzzles and learn to love patterns, then you can learn to love math. That was example 5. One more. Example 6 talks about using the binomial theorem to expand a power. Okay? So this is exactly like what we just did. To identify the values in row 3 of Pascal's triangle. So we can scratch out Pascal's triangle anytime. So for row 3, Pascal's triangle, you'll see over here you can. Starts with a 1, then there's 1 and 1, then there's 1, 2, and 1. This is actually row 0. This is row 1. This is row 2, so we need one more. Row 3 would be 1, 3, 3, and 1. This is the one we need for our example here. So identifying the values in row 3 of Pascal's triangle. 1, 3, 3, and 1. Okay? So we expand the power as described in the binomial theorem using the values from Pascal's triangle as coefficients. So we know our coefficients are going to be 1, 3, 3, and 1. And we know that the exponents are going to start with 3 for the s and go down. So this is 3, 2, 1, and 0. And for the negative 2, which is serving as our b, it's going to start at 0 and go 1, 2, and 3. Notice that since we're cubing this, the sum of my exponents is always 3. Hopefully all are still with me. Anything to the 0 power is 1. Okay, so if we're multiplying by 1 anyway, we can just kill that. And we can simplify here. 1 times s cubed is just s cubed plus, this is 3 times s squared times negative 2 to the first power. Well, negative 2 to the first power is negative 2. Negative 2 times 3 is negative 6. Okay, now for this term, we have 3 times s times negative 2 squared. Negative 2 squared is a positive 4. 4 times 3 is 12. And we have an s. And for our last term, we don't need to write the 1. And this is a 1 also, so all we need is negative 2 cubed. Negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is 4, times negative 2 is negative 8. So we're ending with negative 8. So understanding our pattern, understanding our Pascal's triangle, we can expand these binomials a little bit more quickly. Okay? So now we have part B. And I just noticed that we're 18 minutes in, so I'm going to go ahead and stop this and we can do one in class.